speaker is Professor GuanHua Chen of the Department of Chemistry at the University of Hong Kong. He's going to speak on multi-scale simulation of emerging electronics. Professor Chen is the head of the chemistry department at Hong Kong U, and is also the courtesy professor at the Department of Physics. He got his PhD from Caltech, not MIT, and he has been very interested in nano-electronic transport, and is one of the key players in this project. Let's welcome Professor Chen.
Thank you also for kind introductions. Maybe start. All right. So now, in fact, I'm in chemistry department. Okay. This is I teach advanced physical chem. Okay. So this is the first slide I use for my course. Okay. So this is what Dirac said in 1929. Okay. Dirac basically declared the underlying physical laws necessary for the whole chemistry, okay, was known, and also for the most part, okay, of the connection physics. Okay. So what did he mean? Okay. Basically, this is the equation you need to solve. Okay. Right? So everything about chemistry, in fact, material science, connection, okay, bulk of the physics. So in fact, but the problem was it's very difficult to solve. Okay? The hydrogen atom can do it, but with the computers now this has changed quite a lot. We now routinely solve this on computers and to interpret experimental results. Okay? With this. All right. So we've been used in a lot, very successful. Okay. But for our ultimate objective for this computational chemistry is, in fact, predict, okay, before the experiment, okay, and better to design, okay, to design new material, design maybe device. So now, this is a Nobel Prize in chemistry in 1998. It was given to a physicist, Walter Cole, and John Popple. John Popple actually was trained as a mathematician, okay, from an applied mathematician, okay, and Cole was a physicist. Okay, for their contribution for first principle method, basic functional theory. Also, computational method in quantum chemistry. Okay. So at the time, in fact, this is actually how to put this. In fact, when I started my PhD. Okay, I did my PhD with Bill Goddard in theoretical chemistry. We can only solve, okay, the quantum equations, solve electronic structures of very small molecules. But this has changed a lot. In 1998, this field was so successful, the Nobel Prize was given. All right. So at that time, I thought, okay, maybe it's ready. Okay, we are ready to use this to really to predict. So this is what I did in 2000. At the time, there was in the midst of IT field. Okay, so I wrote this business proposal called SIN Lab Corporation. Basically. What I propose to do is to to solve, use these computational tools to solve problems for materials, pharmaceutical industries, as well as maybe for electronic industry. All right. So at the time, I was managed to be able to talk to a few investors. Okay. In fact, I went to Wall Street, New York City. Okay. But I was not successful because these bankers, investors, they were very smart. Okay. They realized it was not ready to do this. Okay. So I was not giving any money. So, in fact, this is the international technology roadmap for semiconductor 2007. Okay. Now, at the time, 2007, we are Intel actually in the late 2007. Intel actually rolled out the 42 nanometer device chip. But industry, in fact, was trying to make 22 nanometers at the time. So it was sort of expected that 22 was going to be rolled out in 2016, but we know actually it was much faster. Right? So now we are using 22 nanometer technology. And this is Moore's law, and it says maybe by in 2020s, we are going to reach physical limit because transistor will get smaller and smaller. Okay. But this is a good news for us, right? Because when the device gets smaller and smaller, we will be able to do calculations. Okay, the quantum mechanics calculations. So this was a really good news. Okay. Then I thought maybe we're ready to do what I proposed. Okay, in 2000. So, in fact, I think 5 years ago, I remember about 5 years ago, okay, there was Fu Chen and I had a lunch. Okay, so after we finished the lunch, we walked back to these buildings. Okay. Then on the way, Fu Chen told me, Paul Chen, which is our pro-vice chancellor, okay, in research, which is the vice president in charge of research of this university, asked him to propose a proposal for area of excellence, okay, which is this project. In fact, in fact, Fu Chen and his colleague proposed a project 3 years ago, before 2007. It was not successful. And Fu Chen said, what do you think this time? Because the deadline, in fact, was just a week away. Okay? He said, what do you think? Then I said, let's do this. Okay? So we came up, then Fu Chen said, maybe. Let me talk to Wen Qiu. So he went and I talked to Wen Qiu, and Wen Qiu said, why not? So then we got together and wrote, I was sort of put in charge to write the initial proposal. Okay. So this is the title of the proposal, was the modeling and simulation of sub-22 nanometer device and integrated circuits. Okay. So we wrote the initial proposal, but to send out, we have to go through a university committee. And the committee looked at our proposal, they said, well, it's good. Okay. But the title is terrible, it's incomprehensible. Okay. So we had to change the titles, and this is eventually the title. Okay. So this is the title, eventually we come up modeling, a theory, modeling and simulation of individual electronics. And so the deadline was 1 week, and really it's not possible. So we asked and for another week, eventually, in 2 weeks, we send out this proposal. So this is the proposal. Okay, we send out. All right. But then at the time, it was really, I mean, putting all the team together, it was really quite effort. Okay. So we, in fact, will put together the team in the last minute, okay, and just in time to submit the proposal. So there were skepticism. Okay, said you guys will never get funded. Okay. Luckily, actually, the initial proposal was approved. Okay. So. And this is, in fact, proposal, and we were invited for the full proposal. This is the full proposal. Okay. I remember the night we submitted the full proposal and the presentations, everything. Okay. So Fu Chun took me and my student out for dinner. Okay. So we were all very excited because we were very confident we had it. Okay, we were going to get funded. But at the back of my mind, that in fact there was a big problem. Okay, I did not share with my students for such time. Okay. So what was this? In fact, this is from the proposal. Okay. The full proposal. So basically, what we propose to do is starting from the quantum mechanics. This is what we want to do. Okay. For quantum mechanics, all the way to the circuit simulations and to the design. Okay. So this is the multi-scale approach. And so how to bridge what we do at atomic scale and what is being done in the engineering and in the industries. Okay. How to make handshake, okay, bridge the gap between these two fields. At the time, we were not clear how to do it. Okay. So what we did, we just said, okay, putting something, a mapping between quantum mechanics and the classical circuit. Okay. But in fact, really, we did not know. Okay. What was this about? And when I went into the presentations, I was very afraid the reviewer was going to drill on us on this. But luckily, they did not. So we got funded. Okay. Now, after we stopped this project, in fact, it was really good, this collaboration between electrical engineering and physics and chemistry. In fact, Manson Chen, one of the key members of this project, came and he gave us a very nice educational seminar on what people do in the industry to simulate this TCAP. Okay. So basically, he taught us what is a compound model. Okay. Basically, compound model is a model to describe ID curve of individual transistors. You can either use lookup tables, or basically you do a lot of experiments, okay, and then you have curve matchings, okay, and by fitting all the parameters in your compound models. Okay. So this is experimentally determined compound model. Once you have compound model, then it's become very easy to do simulation for integrated circuit. So also he taught us how to do this. Okay. Basically, for instance, he taught, this is exactly this. I borrowed his slide. Okay. The first seminar he gave us. Okay. Basically, we have say 4 electronic device. If you know the compound model for each of this, so you can calculate the partial derivatives. Okay. And basically, for the circuit simulations, basically you need to solve this. So this matrix equations, okay, the linear system. All right. That was very clear. Okay. So then all of a sudden it hits me, okay, how to do this. Maybe people knew, but now I knew how to do this. Okay. So this is basically from use our language. This is how we would view in chemistry or in physics. How would we view this the multi-scale electronic automation, device automation, or design automation tools? Basically, this is the number of transistors. This is the size of the system. Down here we have the word transistors. Okay? This is described by the compound model, the IV curves. Okay? Then with IV curve, I either use lookup tables or the mathematical models. Okay? Then you can use this to write down the equation, and then you plug into this circuit simulations, for instance, SPICE. Okay? Then you can simulate the integral circuit. Okay? So this is how the language we would use. And up there you can have logical simulations and all this. Okay? So the key for us is key. Okay? Compound. Okay? This, of course, currently this is mostly experimentally determined. So what we want to do is we want to replace this with quantum mechanics, atomistic based simulations. Okay? This is a Nobel Prize in chemistry. In fact, the last one was 98, so 15 years after the last chemistry prize in theory. Usually it's about 10 years. So, in fact, this year's Nobel Prize is given for the multi-scale models of complex chemical systems. Okay? So you may get lost, but I'm getting there. Okay? Right. So this is given to the three gentlemen. So what this is actually, it's here. Okay? Usually, when you're dealing with biological system, you want, for instance, enzymatic reactions. The system is too big. You can't do full quantum mechanical simulation of this. Okay? So what these gentlemen proposed to do was, for the important region where the chemical reaction occurs, you use quantum mechanics. Okay? The rest of them, you use molecular mechanics, classical mechanics. Therefore, you can deal with entire system. And this year's Nobel Prize in chemistry was given. Okay, this is what we learned how to do it. In fact, again, this is another example, the collaboration between engineering and science. Okay? In fact, I think this was Alex. Okay? Again, he was recruited in the early days of this project, and he came and gave us a talk, again, lectures how to do this TCAT simulations, how to use just diffusion equations to simulate the current through a semiconductor device. Yet again, we're sitting there and listening and down, because if you want to do this use computation simulation to build up this compound model, the method you have, it has to be fast enough, very efficient, and yet we want a quantum mechanical base. After listening to Alex's talk, I realized maybe we can do this. Okay? So, for instance, this is the device, okay? And the rest of the substrate. This is the lead. Okay? Kind of thing. So for this part, we use quantum mechanics. We have heard this NEGF method, Green's functions, and you have to solve this with Poisson equations. Okay? The rest of this, you use what Professor Mark Rundström said yesterday, the diffusion equations. Okay? That's the exact equation, similar equation you see. Okay? And now also for this part, we can solve for the either Poisson equations or for the time domain, frequency domain, we can solve Maxwell equations. When shown, I said earlier. The key is the boundary condition of the interface between the quantum mechanical regime and the what I call classical or EM regime. So this is what we do. Actually, for the quantum mechanical regime, we use the potential coming from the drift diffusion of Maxwell equations as a boundary conditions. Okay, for the QM part for the NEGF calculation. As a result, okay, the charge and the potential across QM EM regime they are continuous. Okay, it's very important. For the EM regime, when you calculate, you use the current densities coming out from quantum mechanics calculation. This is for the NEGF as a boundary condition for the EM simulations. With this, the current are continuous. Okay? Current distribution continues between the quantum mechanical cross interface. So with this, you ensure both the current charge distribution as well as potential distributions are continuous in this across QM and EM interface. That's very important. All right. So after we publish our paper, test our result method, we decide to test something new. Okay. So this is what we decide to do. The junctionist say transistor. Basically, usually the CMOS you have PNP or NPN, so you have PN junctions. Okay? But this type device, in fact, you just have a narrow band. What controls it is the gate. Is actually what the Professor Mark Longstrom lectured us. Okay? Just control the gate voltage. I mean, so you can control the conducting channel, the potential. And you then can shut the. Then you can have on and off transistors. Okay? And this is the result. Okay? So basically, this is for a P-type, for instance. Okay? When the gate voltage is 0, the current is off, or when it's 1, it's on. Okay? Or for the N-type, okay, when the gate voltage is 0, when it's 1, it's on. So this is actually the order of magnitude is about 6 or 7. So it's very nice. So we decided to use our method and look at this. And this is a paper published in 2000. This was 2009. This is 2011. Okay. And this is the silicon nanowire. Okay. If you look at the dimensions, this is about 5 nanometers. Cross is about 2 or 3 nanometers. Okay. So we try to use this experimental junctionist transistor, and I want to do our simulation on this, okay, periodic simulation on this. So this is the system we look at. So this is the cross section. Okay. This is the QM regimes. So this is the silicon metal wire. So the width here is 2.5 nanometers. Okay. The height here is 5 nanometers. This is exactly the experimental geometry. And in quantum regime, actually, the size of a quantum regime can be it's about 20, 30 nanometers. Okay. The overall length of the systems is vary from 37 to 157 nanometers. So in our quantum mechanical regime, we have overall 15,000 atoms. 15,000 silicon atoms with only 4 dopants. 4. Okay. So this actually gets us to the experimental doping density. Okay. The method, the quantum mechanical model we use is called DFTV method. It's approximate DFT method. All right, so this is the IV curve with the green line. Okay, this is what we obtain. Okay. So when it's the gate voltage is 0, well, there is a reference point. Okay. But anyway, this is when it's on, it's about 10 to the minus 6. When it's off, when TV is off, it's about 10 to the minus 12 or 10 to the minus 13. So it's about 6, 7 order magnitude. Okay. So, but if in the early days, when our method was not fast enough, okay, we say we would be able to use 3,000 atoms, you will find yes, you have when there's on and off, but the order magnitude only differs about 2 order magnitude, not like 6, 7. So, but once you get the doping density correct, you got 7 order magnitude. And so this is qualitatively agreed with experiment. If you also look at there's sort of kink here, right, for this particular configurations. In fact, we can understand this. Okay? For instance, at bias voltage is minus 0.7, okay, it's about here. Okay. This is a 2 dopant, okay, local density of state. This represents 4 dopant atoms. Okay. They are in the bias windows, okay, so the current is slightly higher. Okay. But for 0.9 here, okay, there's 2 dopants out of the bias windows. Therefore, the relatively, you look at the current is lower. Okay. Then this commercial software predicts. Okay. So in fact, we submit our paper and the referee insists us to explain, okay, clearly why this is happening. There is some kink. You can really look at the local density state to explain all this. All right, so then we put in electron phonon couplings and all this. Okay, and then this is the result. We end up with this. Okay. This is a 0 bias voltage. Okay. This is 1, and this is the experiment. So let's look at the comparisons. In fact, very nice. Okay. Order magnitude is certainly correct. Okay. So the message here is if the doping density is right, okay, in fact, we can reproduce the experimental result. Okay. Same order magnitude. So we are very happy. Then now we're ready to construct a compound model. Okay. So this is the compound model we construct, and there's a blue line here. The red line is our QMEM calculation. Okay. Now with compound models ready, as I explained earlier, okay, we should be able to do circuit simulations. Okay. So in fact, we actually use SPICE to do our simulations. This is a very simple integrated circuit. It has 2 transistors made of junction. So this is the inverter. When the current with voltage is high, the outcome voltage should be lower. Or if the incoming voltage is lower, outcome should be high. And this is exactly what we observed. Okay. So this is the blue line represents input. Okay. The green line represents output here. So when the input is low, output is high. When the input is high, output is low. This is coming out from the SPICE simulation. So now this is our views about what is the next generation EDA tools should look like. Okay. Down here it should be this QMEM based compound models, okay. And it with compound model already established, we can use it to do circuit simulation. And for compound model itself, in fact, it's a multi-scale model. Down here we have DFT, and there is pi bounding type, and this is QMEM. Okay. So we need to do, because for engineer, you need to do very fast, very efficient. This is what we do. How much time do I have? Okay. Now, very quickly, I want to tell you another story. Okay. the first principle method for transient current. So basically, we want to use first principle method to calculate time-dependent current. So this is our work is based on what we call holographic electron density theory. This is a very nice theory. Okay? If you, for instance, want to know the electron density in this lecture room, this theory tells us all you need to know is electron density in your little fingers. It's mathematics. Okay? If you're interested, I'll be happy to explain this to you. So this tells us, in fact, we can develop a first principle method for the electronic device. The input, all we need is the electron density of the device, not the limit. So let me tell you the theory. Eventually, we end up with this theory. Okay? It's a Liouville equations. So this, for instance, this is the electronic device we're interested in. This is the left lead and the right lead. Okay? And you can write down the Liouville equations, Liouville-Van-Neumann equation for the system, device plus the electrode, then somehow integrate out the electron. Okay? Eventually, you end up with a set of exact equations. Okay? I will not go through in detail again. Okay? Basically, this you had a three set of coupled equations, and this is exact. Okay? So eventually, this is what you do. Okay, for those of you who are interested. Basically, you solve this three coupled equations, which I just use this equation to simplify, okay? Coupled with Poisson equation. Okay, the only boundary condition you need, okay, is the boundary condition for Poisson solving. That's it, not this equation. As if you solve this for isolated system. In fact, let me put it in context, okay? Because some of you are electrical engineers. Okay? In fact, what we really do actually is a quantum version of Boltzmann transport equation. Okay? In the 1980s or 1990s, people actually tried to do this. Okay? This is called the quantum kinetic equations. Basically, what people do is try to solve the Wegener distribution, right? This R, K, momentum, this displacement time. Okay? In fact, we did this, but in a different way. The problem at the time, actually, this was eventually sort of gave up, okay? Because the boundary condition. The boundary condition they need match the boundary, the Wegener distribution function as a boundary condition is very difficult to do. But in our case, we have a very simple boundary condition. Therefore, now we can do it. So now we have a full quantum mechanical version of quantum transport equations, and we can do it in time domain. And really look at it. So just give you some application of a method. Okay. For instance, what we did is here. There was a question whether the DFT NEGF was correct or not. Okay. So one motivation for people to do time-dependent DFT was because they said this DFT and NEGF is not correct. Okay. But this is we decided to do this, and this is two systems we look at. Okay, for different bias voltage, okay, different rate to turn on bias voltage. Okay. And for different cases, in fact, you reach the same steady state. Okay? And the same steady state, in fact, is exactly what the non-analytic formula predicts. Okay? In fact, you can prove this analytically. Okay? In fact, if you take time into infinities and assume there's one assumption, okay? Assume there is steady state. Okay? But there are cases, maybe there is no steady state. Okay? It's possible, mathematically it's possible. If there is a steady state current, you recover the non-analytic formula. So this is exactly our numerical result. Use our code. The code line is ready. We can just use it. Another thing we look at, actually, we can also compare our time domain result with the first principle AC quantum transport calculation. We can verify. Okay, this is our method, TDDFT method, and the triangle and the square is AC quantum transport theory. In fact, now we know how to do AC quantum transport. Again, with help of this method. Another thing we look at in collaboration with Mark Reitner, actually we look at, for instance, molecular electronics. Okay, he's still interested in this. I agree with Professor Chen. We can learn a lot by looking at this. Okay? Whether we can do it or not, maybe. Okay, maybe. Okay. So basically, what we look at is this benzene ring, and there's two electrodes connect at the metal position. Okay, this is source, this is drain. Okay. So if you look at this, let's forget our third electrode for a moment. Okay, you will find actually the current going through this is zero. Okay, because there's quantum interference. Okay. So if you look at this with time domain result, at time equal to zero, we turn on the bias voltage. If you look at this, the current is zero, the steady state. Steady state very quickly, few frames per second, we reach steady state. Then what you can do is you introduce this probe, okay, what we call, what people call this the Buteyko probe. What this Buteyko probe does is actually it's a dephasing mechanism. So if you introduce this Buteyko probe, the current is order 6 orders magnitude larger. So this can be used as a transistor, a controlling mechanism. Okay. And we can also look at the correlation between current and coherence, because time I have to skip. So another thing we can again look at is the memories. Okay. So this is in fact we are working with writing paper with Leo Trump. Okay. In fact, we found this system in fact has a memoristic behavior. Okay. Again, if you're interested, I'll be happy to talk to you more because time I will skip. So, okay, finally, the acknowledgement. Okay. So these are the people, member of my group, who worked on this multi-scale method, as well as this time domain method. Okay. And many of them has moved on, taking real jobs. Okay. And these are the collaborators. The blue Alex is in the audience. He was the person who initiated this multi-scale simulation. And Professor Jiang. Okay, I think maybe he was in the audience. Okay. And also Professor GuanHua. And actually, GuanHua now is moved to Fuji University. Also, we are working with Tom Bernheim from Bremen University. Basically, we're looking at this DFTB models. We want to improve further. And with Professor Chu, we're working on this multi-scale method. Okay. And we are working with Bill Goddard, Mark Reitner, and Bill Trump by using this time domain method to look at different systems, okay, different phenomena. With this, I thank you for your attention.
Thank you. And now it's the Q&A section. Are there any questions for Professor GuanHua Chen?
Yeah, you mentioned about for the quantum mechanics, you provide the current to the electromagnetics. So this current should be distributed in all the quantum mechanics regime, or just the surface of the two regimes.
It's just surface on the interface as a boundary condition.
As a boundary condition.
Yeah, it's only on the boundary condition.
We know the quantum current is can be, if you get a wave function, we can know the quantum current because the wave function are volume distributed. It should be every point has current. How to get the surface current? I want to know.
No, when you calculate solving NEGF calculations, okay, from solving the quantum mechanics calculation, in fact, you can calculate the current. Okay. Current basically is the wave function times the gradients of wave function.
Right.
Yeah. So you will end up with a current density. So from this of course the entire volume, but all we need is at the boundary.
Okay. All you need
at the
is
boundary
boundary.
condition.
Okay.
So that to ensure the current distributions are continuous across the interface.
Okay. Thank you.
Yeah, any other questions? Yes, Mark.
So I'm curious about the time-dependent calculation.
Okay,
The
I know you should.
The transients you're showing are on femtosecond.
That's right. That's right.
So are there experiments? I mean, I guess typically if they're electrical, the
Yeah,
parasitic slow everything down.
Yeah, I totally agree because now the experiment they can do at up to 10, 20 terahertz. It's still slower than this. Okay, but for us, it's mostly the theoretical explorations. Okay, try to learn. But if you really want to do experiment, you can do that for the quantum dots. Okay, then the time scale, the coupling is in the milli eV. Then it's 3 orders of magnitude longer. Then, in fact, for some of our calculation, we did propose some experiment to verify.
But your simulations contain phonons?
Yes, we
That's to slow things down.
that's right. Yeah. No. In fact, the phonon right now we use it just include the self-energy calculation. We do not include it explicitly. But we are developing this what people call the very fast dynamics. Okay. In fact, you can see you simulate the nuclear motion. Nuclear is in the picosecond regime, but electronic they're very fast. They really just follow the phonon motion. I mean vibrations. Very fast.
I guess, thank you very much. Next speaker from the AOE project is